So this one is on carbon and the molecular diversity of life. So carbon is going to be the main structural framework that all life forms are made up of as we know it on Earth. Now, on another planet, who knows? I mean, they have found bacteria on Mars. So, yeah, there are Martians. They're just bacteria, but they're there. But what we know of on Earth is based on carbon in there. So when we talk about organic chemistry, that is the branch of chemistry that specializes in studying carbon compounds or hydrocarbons in there when they look at it with hydrogen and carbon together. So if you go on to a university to study chemistry, you generally do a year of general chemistry and a year of organic chemistry in here. What you would take here with the chemistry class is just a introduction to general chemistry, but they have a whole year series, and to do the full year series of organic, you get to do the full year series of general beforehand all the time. Vitalism is this belief that there's a life force outside of the jurisdiction of physical and chemical laws, and this used to be the dominant theory of how we looked at life in there. It was foundation for the new discipline of organic chemistry, but as they started to be able to create different organic chemicals in the lab, they realized, oh, you don't have to be alive to do this. So one of the things that they made that set this idea and started to chip away at this foundation was they made urea without a kidney. Why somebody decided, oh, I want to make fake urine or something in here in the lab, I don't know what was behind their motives in there, but that was what kind of was the wake-up call to them, and they said, oh, no, you don't necessarily have to be alive to make these chemicals in there. So what happened is the view gradually shifted to more of a mechanistic view in here, that the physical and chemical laws govern all natural phenomena, including life processes. So the things that are actually alive, well, that one's still a hard one to explain in there, what makes you alive and what makes you dead, because there is no chemical change that we can detect in a body that's alive versus dead in those few seconds of change in there. So when we look at the carbon forms in there, carbon has kind of a unique structure. It's got the 6 electrons. So that means 2 in that first ring, 4 in that outer ring, 4 empty holes here. So that means carbon's going to bond with 4 other things, and we generally draw it like that with 4 legs on there as what that represents in there. And it's going to form 4 covalent bonds in there till it has 8 electrons available. It's going to form a tetrahedron with angles of 109.5 degrees when it forms 4 singular covalent bonds. So that's what this is showing here. So when we name carbon compounds, the naming of them is actually really easy in there. If it's got 1 carbon, it gets the start of the name meth. And it's not like meth lab in Pierce County. It's like methane in there. 2 carbons is F3-prop-4-bute. So that's just an easy one to remember in there. When you're naming things, that's probably the easiest system in there, the meth-F-prop-bute. Then you look at the number of bonds in there. If it's got single bonds, it's going to have an ANE ending. Double bonds, ENE ending. Triple bonds, YNE ending in there. So if you have propane, how many carbons are you going to have? 3. Single bonds, double bonds, or triple bonds? Single bonds. So if you have butene, 4 carbons, single, double, butene, double bonds in there. So it's real easy to use the names like that. You can look on the back of bottles or food packages. Yeah, you'll find those names on your food packages in there, and you can go, oh, now I kind of understand what that means when you see methyl something on there. Oh, it's got 1 carbon of some sort on there. Or if you see ethyl, it means 2 carbons in there. So these are just some structures of what they look like in there. So these carbon chains are going to form the skeleton of most of the organic compounds. They'll vary in length in there. They can be straight or branched. They will vary in the number of bonds, and then they'll have additional elements that get bonded to the skeleton. So here you've got ethane, 2-propane, 1-butene, 2-butene. What this 1 and 2 mean is that there is something additional, or that's where the double bond is between the first, after the first carbon. Here the double bond is after the second carbon in there. So we just use numbers to distinguish where these things occur on there. So 2-methylpropane, what this means is on carbon number 2 there is a methyl group here, which is this carbon with the 3 hydrogens in there. It can also be called isobutane because there's 4 carbons, and iso is an alternate arrangement in there. And then when you have it be circular in there, cyclo usually gets put in there. Hexane, hex for 6. Benzene, in here you've got 6, but you've also got every other bond is a double bond in there. So hydrocarbons are going to consist only of carbon and hydrogen. These are a major component of petroleum because it's something that's partially decomposed in there. The nitrogen products have been decomposed, and what's left is the hydrogens in there. And that's why we burn petroleum products in there, is because these are going to have a large amount of energy in there, and you can burn off the carbons, and they'll be released into the air as carbon dioxide as you start to burn them off and break the bonds between them. They are also hydrophobic in there. So if you look at this, does this look like it's uneven, or does it look pretty symmetrical? Pretty symmetrical. There's no positive or negative charges on there. But remember, with the water, you've got your partial negative, partial positive on there. So you've got polar ends in there. It's not symmetrical. So isomers are going to be variations in the architecture of the molecules in there. So the structural isomer, they have a different covalent arrangement in the atoms in there. So here's an example of a structural isomer in there. You've got your 5 carbons all in a line, or you can have 5 carbons and one of them branches off to the side. You've still got as many carbons and as many hydrogens. They're just arranged slightly different in there. A geometric isomer is going to have the same covalent partners, but in different special arrangements in there. And I believe that term was supposed to be spatial arrangements. So with these, here you've got a double bond in there, so that's going to be 2 electrons. Then you're going to have an electron pair shared here and 1 shared here. That's why you come up with only having 2 attached to each carbon, is it's attached to the neighboring carbon twice. If they are on the same side, the legs are on the same side, we refer to that as a cis isomer. If they're on the opposite side, we refer to it as a trans isomer. So can you think of something you encounter on a daily basis where you see the cis and trans isomers? Think about going to the grocery store. On a food label. Having to do with fats. So you'll see things where they talk about now that it does not have 0 trans fats in there. What happens in nature is you're going to naturally have a combination of these in there. And your body is meant to deal with a combination of things. But one of the things that they found was that if they artificially hydrogenate fats, they will live on the shelf longer. So anybody have any Crisco at home? Or maybe your mom has some Crisco. I know my mom still does, even though I throw it away, she seems to go and buy more. It never rots in there. And, you know, that's one of the few things in my mom's pantry that isn't rotten. I found food from the 80s back in there. So, and I mean, when I looked at the Crisco thing, and I'm like, they're not wearing low-waisted pants that came from this decade in there. That is some old Crisco. She goes, your grandma gave it to me. That's just wrong. So I opened it up and looked. Any mold on it? No, nothing. Looks exactly like it was. The stuff does not die in there. So that's why the food industry liked it, is that it would work for a long time. However, do you think it's going to take different enzymes to break this down? Yeah, so if you remember last time where we talked about there was the endorphins and the morphine, that they looked like they were the same shape. That shape is really important for being able to break things down. Cis and trans don't get broken down the same in the body. So it actually changes properties of your cell membranes. And when that stuff's floating around in your bloodstream, one of the arguments they had is, well, it's not a saturated fat, so it's going to be better for heart disease. It's actually worse because your body doesn't break it down in your bloodstream. It just floats around in there longer and you can't even deal with it in there. So now that people have become more aware of it, this knowledge has been out there for at least 20 years that it was harmful to your health. However, it wasn't widespread, so you didn't see it being advertised in packages. But now that the public has become more aware of it and is starting to avoid things that have it in there, now they'll use it as an advertising thing in there, that it doesn't have any of the trans. So cis is together. Think of it like sisters together. Trans are apart. So another type of isomer we have are the enantiomers, and these are ones that are mirror images. Your middle carbon has to be asymmetrical. So that carbon in the center has to have different things attached to it in there. If it's all hydrogens, it doesn't matter which way you look at it. And so we think of it as a left or right-handed version in here. And so you can see here that you've got all the same things attached to it. And this has to do with the direction it would spin light, is how these come about in there. So they're just mirror images like your right and left hand are on there. And so those are going to behave differently in the body as well. And one example of this was the drug thalidomide in there that was used several years ago. And the good enantiomer, the one that you wanted, had the desired effect. However, when you put it into the patient's body, some of it got converted into the other enantiomer. It switched it around in there. And that's where the problem was in there, is it started to cause birth defects in there, very severe birth defects. And they were giving it to pregnant women for morning sickness in there. Thalidomide, it is the drug that they were giving people. Yeah, it would have maybe been, most of you guys are probably too young that it wouldn't have been around anymore when your moms were pregnant. My mom could have potentially taken it, but she didn't. She just had x-rays when she was pregnant with me. Bad enough. But it would cause very severe birth defects in there. I mean, they were really severe birth defects. A lot of times the baby wouldn't make it, missing limbs, things like that. So it got pulled off the market, but they do actually, they've put it back on the market now, and it's not used for pregnancy anymore. It's used with certain cancer treatments in there, and when a person, they've used it for some other diseases as well. If a person is going to be on thalidomide, it's mandatory that you're on birth control at the same time in there. So if you get it, you're basically, you have to take a pregnancy test every month. You will get a prescription of birth control if they can give you an injection of birth control so you don't forget to take your pill, or give you something even more permanent than a pill that we don't have to worry about patient compliance being a problem. They'll do that with it because of the difference in there. But that's a very profound difference where one drug can have a very severe effect in the body based on is it the right or left enantiomer in there. So in organic chemistry, we have these functional groups that are going to replace one of the hydrogens on there. So if you've got this long string of carbons, most of these might be hydrogens on here, but you could also stick something else on here. And when you put another functional group on there, sometimes we just refer to it as R in there for the functional group other than hydrogen. Those are going to give different properties to that in there. And so they will participate in the chemical reactions. And part of what is done in an organic chemistry class is your first quarter, you're learning the names, you do the meth, eth, pro, bute thing, and you're like, oh, this is easy, this is going to be way easier than the last year chemistry was. And then you start learning the different reactions that you go through to build different molecules, putting these different functional groups on there. And the class gets drastically harder, and it's just a real slap in the face to you. So in biology, we have 7 functional groups that we talk about. There are more than that out there, but being that we're in biology, we don't care about the other ones in there. So the hydroxyl group is going to be one of the more common ones in there. It's going to put a hydroxide or an OH in place of one of the hydrogens. So that would get attached on there. And that's what is done in the alcohols. So an example would be ethanol, where you're going to have 2 carbons. You've got hydrogens on most of those legs, but on one of them, you have the hydroxide. So switching that makes it ethanol. You've still got the eth for 2 carbons on there. What that's useful for is it's going to create some polarity so it can bond with water, and it can help dissolve organic compounds. So if you have something you're trying to dissolve in water and you're going, this isn't dissolving in here, let's try throwing some alcohol and see if that will dissolve it in there. And that will increase the solubility in a lot of things. When somebody, this is a horrible example, but I can't come up with something better in here. If you're going to get drugged by somebody without you knowing, one of the reasons they try and stick it in alcohol is that's going to absorb that substance, where if you open up one of your pills and you try and absorb it in water, probably not going to absorb in there. You can probably dissolve it in alcohol in there, and that's why a lot of people get drugged via alcoholic drinks in there. So the carbonyl group is going to be another carbon and an oxygen that will attach in there. This is going to make your ketones. So it's called a ketone when it's within the skeleton. It's an aldehyde when it's on the end. So for making things like acetone or propanol, your aldose or ketose sugars in there. The carboxyl group is a carbon, 2 oxygens, and a hydroxide in there. That's used to make some of your organic acids in there. Carboxylic acids, acetic acid, which is vinegar, is an example. It will give whatever you're making some acidic properties in there. An amino group is going to be a nitrogen with 2 hydrogens on there. It's going to make an amine. Glycine is an example. These can act as a base at times when they're going to be ionized with a +1 charge in cellular conditions. The sulfhydryl is going to add a sulfur and a hydrogen. These are the thiols. Cysteine is an example of one of those. The thiols or sulfhydryls are important in biology because they make really strong bonds. So things that are strong materials are going to tend to have more of the sulfhydryls in there. So it's going to help determine the curliness or straightness of hair. There is a fair amount of sulfur in fingernails in there. That's what makes them hard in there. Also making some of your ligaments and tendons in there. So if somebody has a musculoskeletal injury, a lot of times having some extra protein that is high in the amino acid cysteine in there will be a way of giving your body a building block it needs for the sulfurs in there. So the phosphates, we've got a phosphorus for oxygens, and it has a negative charge on there. We've got the organic phosphates, glycerol phosphates. It's going to help give a negative charge to molecules. It also has a strong potential to react with water and reacts violently. So something you'll see this in later on is your ATP adenosine triphosphate in there that we use as an energy transferring molecule. And because of those phosphates on there, it will react in the presence of water and release lots of energy. Methyl groups. So this is when you have another carbon in the CH3 on there. So your methylated compounds. One of the things we know we use the methyls for in biology is you can attach these onto the DNA and it will regulate gene expression a little bit in there. So these are just some more pictures and examples of these. What you would want to know is you're going to want to know the chemical group and the structure. So I do know that'll be on your first test, knowing just these first two columns of it. I'm not going to ask you anything from these three columns.